Very good morning, everyone. On behalf of Shastra Deemed University, Tanjavur, I invite all for the National Science Day Award lectures. Today, we have with us Professor Ashok K. Ganguli, who will be delivering a talk titled Design of Nanostructures for Energy and Environmental Applications. Professor Ashok K. Ganguli is the Deputy Director, Strategy and Planning at the Indian Institute of Technology, New Delhi. He is also the Institute Chair Professor at the Department of Chemistry. He is also associated with the Department of Material Science and Engineering at IIT Delhi. He was the founding director of the Institute of Nanoscience and Technology at Mohali. He received his PhD degree from the Solid State and Structural Chemistry Unit of the Indian Institute of Science, Bangalore in 1980 in the area of thallium-based high-temperature superconductors. He has been a visiting scientist at the DuPont company and also a postdoctoral associate and visiting scientist at the Iowa State University in USA. Professor Ashok K. Ganguli and his lab works on the design of nanostructured materials for applications in water purification, solar energy conversion, and microfluidic devices, and also on high temperature superconductivity. He has published more than 370 papers with the cumulative citation exceeding 5,400 and H-index of 42. He has successfully completed several research projects funded both by the government agencies as well as from the corporate. He has received several awards. To name a few, he has been the recipient of the National Award of Nanoscience and Nanotechnology given by DST Government of India, the Chemical Research Society of India Medal, Materials Research Society of India Medal, the CNR Rao CRSI National Award, and Chemical Excellence Award. He is also a fellow of the Royal Society of Chemistry London and the Indian Academy of Sciences, the National Academy of Sciences, and the Asia Pacific Association of Materials. Professor Ganguli is a very key member in popularizing science in the schools and colleges. While he was in Institute of Nanoscience and Technology, Mohali, he initiated an outreach program and visited more than 300 schools in the rural area. He is also a speaker in the Inspire series of lectures of the Department of Science and Technology. So without taking much time, I request Professor Ashok K. Ganguli to deliver the talk. Welcome, sir.
Thank you. Thank you, Dr. Rajan. So I first would like to thank the Shastra University for giving me this award lecture. And I'm really honored because it is also been named after Professor C.N.R. Rao, who was my teacher and mentor, and amazing human personality who has touched the lives of several Indian and foreign scientists. So I am deeply indebted to Professor Rao for having trained me, and I have imbibed some of his traits which help me in going about in my daily discharge of duties as a professor and also as an administrator. So today the topic what I have selected is the design of nanostructures for energy and environmental applications. This work I have been doing for say around last 8-10 years, and the kind of work which I'm going to present mainly is the work done over the last 3 years. The students and postdocs who worked and whose work I am going to discuss is mentioned below. And I have got funding from government agencies like Nano Mission, the ACRB, and CSIR. And also IIT Delhi Nano Facility is funded by MIT, that's the Ministry of Electronics and Information Technology, Government of India, which is a large facility in IIT Delhi, like in IIT Bombay and elsewhere, and which has set up the nano facility. Now, apart in nanomaterials, I am basically a synthetic materials person, and I like to design and synthesize materials. And among that, in nanomaterials, the specific interest in my laboratory is to look at the control of size and shape, porosity of nanomaterials and their applications in several areas, mainly in photoelectrochemical devices. And that is what I'm going to discuss mainly. But of course, we also have studied the properties like magnetic properties and like adhesion and other properties on coatings, etc. So some of my review articles are mentioned here for more details. I've also done some work on making microfluidic channels in which the nanomaterials are coated inside, and then we do online photocatalysis and photoelectrochemical applications. Apart from nanotechnology related work, my other interests are in oxide materials and also superconducting materials, which I'm not going to talk today. So in nanostructured materials, as you see that there are four core areas. One is understanding the growth. That is fundamental work, how a nanoparticle grows, how does it convert into itself from a spherical shape to a larger spherical shape or to a rod or to triangles, etc. The other is how do we convert it into some applications, and that's one example I'll give on a low cost water purification device. And the other is how to convert some of the waste into nanostructured materials which can be used in several applications. So that is waste to wealth conversion. Okay. So if you look at the work, growth of nanostructures is one of the area which is fundamental, and we look to the understanding of how a nanoparticle grows through various techniques. And the other is the applications in clean energy and water purification, which is through adsorption as well as photocatalysis. And the final thing is with waste to wealth. So fundamentally, a lot of my research in the lab has grown in nanomaterials design over a large period, starting from 1999. And I have one of the key methodologies I have used and developed over these years is to take surfactants and try to make droplets, which are called reverse micelles when they aggregate in a spherical fashion with the polar head group inside and the nonpolar tail outside. So these surfactant molecules in the presence of water and a non-aqueous medium, that is an organic medium, will create this kind of spherical droplets. It may create other structures also, depending on the phase diagram, which we study, like in physical chemistry, to understand the different structures which are possible as a function of the concentration of surfactant or the concentration of water and the non-aqueous medium. Apart from the surfactant in this chemistry, a very vital role is played by the co-surfactant. So together, the co-surfactant, the surfactant, the aqueous phase and the non-aqueous phase, it becomes a quaternary phase system. And in physical chemistry, we learn how to make phase diagrams and to understand in various regions of the phase diagrams how different such structures can be made. Once you know where you are getting this kind of droplet structure, that part of the phase diagram, that means that those coordinates of the concentrations of surfactants, water, and non-aqueous medium become important for your further use in the synthesis of nanoparticles. The nanoparticles will be designed inside these nanoreactors, which we call. These droplet sizes can be varied by changing different parameters, which I mentioned. Apart from droplets, you can also have cylindrical micelles or lamellar structures and vesicles. So it depends how the surfactants are organizing when you have different concentration of these surfactants and these water and non-aqueous medium. So typically what happens when you mix these droplets, that means you have two solutions of two microemulsions having different ions, and these are inside these nanoreactors. Then when you mix them, these droplets will collide and coalesce, and reaction will happen, and you may get precipitates, which are the nanoparticles. And if you are able to separate them without them getting aggregated, then you can maintain the small size. Of course, there will be a step where you have to remove all these surfactants molecules using centrifugation and washing repeatedly with proper solvents, etc. So a lot of this reaction is happening in the microsecond to nanosecond time scales. And that is an area you can study easily today with the techniques that you have in spectroscopy. But we have also done a lot of work on the post synthesis. That means once a particle has formed, and then you analyze the size, shape, and then you go back and change the parameters again. Look at that is like you are looking at the particle which has formed and then trying to understand. But we have also done time dependent studies to understand as the particle is growing inside the nanostructures. So a large number of materials one can make by appropriate choice of chemicals. So you can see oxides, oxalates, uh, there are core shell structures. When you write CDS at TiO2, it implies that CDS nanoparticle is at the core and TiO2 is the shell. We can make several such materials, and we can make metals, alloys, even borides and sulfides, selenides. I have not shown all of them. So this is one just representative table to show that. The shapes, as you see, from rod to sphere to cube, is being varied. This is an example of the growth of nickel oxalate nanoparticles and nanorods. And we are changing this. The surfactant here is C-tab. The surfactant here is Triton X100. And the non-aqueous medium is also changed. So depending on the type of system that you choose, you can get different size and shape of particles. Even with everything constant, only the solvent effect if you want to see. So this is an example where you change just the solvent, and what you are getting is a change in the length and the diameter of the nanorods. And this is the aspect ratio. That is, if you divide the length and the breadth, you get an aspect ratio is changing from 11:1 to 5:1. So this kind of work one can do. So this kind of work when you are making particles, you want to understand what is happening when the solutions are mixing at that time and how is the growth of the particle taking place. So that we can see that through time resolved fluorescence we have done fluorescence correlation spectroscopy one can use. Uh, we can use dynamic light scattering, electron microscopy, small angle X-ray scattering, NMR. So many techniques are available for one to understand the mechanism during the course of the synthesis, and sometime post fact after the synthesis occurred, you take several batches and try to understand the particle. So uh, what one thing, so this one methodology is shown here. This is the fluorescence correlation spectroscopy, where it is a single molecule kind of examination of the growth of the particle, where you have a confocal situation and you have a laser beam, and basically you have a sample on the cover slide here, and you create a situation such that you have a confocal geometry. And this kind of geometry allows you to see single droplets and single particles, because you are looking at a volume which is very tiny, which is like femtoliter space. So only either one molecule is there inside, or no molecule, zero molecules are there. So you are looking at a very small region. And then you study the diffusion of that, and through this mathematical structure in which is taught in statistical physics and statistical chemistry, where you look at the motion of a particle through either fluorescence or through light scattering, through diffusion. So here we use fluorescence, and this is the what is called the autocorrelation function. From that you can generate the tau, the relaxation time, the diffusion coefficient, and the size of the particle. R is called the hydrodynamic radius, and this is the famous Stokes-Einstein equation, which you can also use using light scattering. But in confocal, this fluorescence correlation spectroscopy, what is important, you are looking at one particle at a time. So what you see, this is an example. So this is a droplet. This is our surfactant molecules, and inside we have this nanoparticle growing, or it is a bare droplet, that means no nanoparticle. And you put a dye, here it is sulforhodamine dye, which is negatively charged, and it sits close to the positively charged head group of the surfactant, which is C tab. So the dye, when it fluoresces, basically you know what is happening to the at the interface, and you basically move when this reverse micellar droplet with the dye is moving, you are looking at the fluorescence, and the fluorescence intensity you can mathematically model, and you can get the numbers which I showed in the previous slide. So this is how FCS gives data, and you can simply see that if you put the dye only in water, then you have the relaxation is it's very fast, whereas if you put the dye inside the droplet, then it is slow. And so you can understand the dynamics of the motion of such particles using the fluorescent probe. Using that, this is the result. When you analyze, you can watch that we mixed reverse micelles with Fe iron ions and oxalate ions, two droplets, and mixed them, and we are following using FCS. Then you can see that nanoparticle growth occurs, and this is a slow reaction actually. It takes some days, and then you get particles of different size, and the red dots show you the FCS data, and you can see that the growth continues. But however, after some time, the growth you don't see, because in FCS you cannot see large particles. When the particle has grown beyond a certain size, the data shows only some bare droplets. But how do we know that is going beyond a certain? By looking at DLS data and electron microscopy of the particles which we get out of those droplets, which tell you that after a certain size of the particles tend to agglomerate in a direction and then form the rods. So this is how we understand the mechanism of formation of the nanorods in this system. Okay. Now we can also do small angle X-ray scattering. So just telling you another method where you can look at the scattering at very low angles, which is called the small angle X-ray scattering. And using that, you will get plots like that, and you can find out the length and breadth, and the asymmetry of the plot shows that you have a more elongated structure. You can do many other details. You can vary the W naught. The W naught is the ratio of the surfactant is to water. And that if you vary, basically, you are varying how much water in the droplet goes. So if you vary W naught and you vary some other ions to affect the interface, you can get from small angle scattering, you actually get these plots. And from that, you do some modeling, and you can get the size and shape of these droplets. So the uh, W naught parameter is being increased, the droplet size is increasing. Here R is some ion we have added to affect the interface. So this is the interface, right, of a droplet. And if you put some additional ions, they will go and interfere there. and the droplet structure will be modified. And that is what we do. We add an ion called salicylate ion, and as the concentration of that ion is changing, we can vary the shape. So you see these are more elongated, ellipsoidal, and at some W naught, they tend to become more round. And so these, with these two parameters playing, we can get several shapes. And now if you make particles in these, you will get different types of shapes. So that's the idea. This is more details. And this interface and what kind of water is at the interface, what kind of water is at the center is a very important topic of research, not only in this kind of chemistry, but also in life sciences, in protein folding and protein aggregation and all that, where you study the interfaces. And here we have also looked at NMR to explain how the interface, this curvature changes. So the curvature changes, basically changes the shape of the ellipsoid. Okay. Now let me come to, so that was some fundamental thing that we do using spectroscopy or small angle X-ray scattering or DLS or NMR to understand the shape of the droplets, and we make nanoparticles. Now, making the nanoparticles by some of these methods, sometimes we also use hydrothermal methods, which I'm not going into now. We make nanoparticles, and the application today I'm discussing is to look at solar energy conversion. So basically, plants use solar energy and convert into fuel. And in physics, we study semiconductor physics, where we study PV or photovoltaic cells, right, or solar cells. And in chemistry, we use semiconductor liquid junctions. And so in an electrolytic kind of situation, we study use of light or conversion of solar light, use these photons to generate hydrogen, oxygen. So water splitting reactions one can do. So what is the basic science behind it? So if you have a semiconductor photocatalyst, so the key area is you need a semiconductor photocatalyst. That means you need a material which will absorb light, and that absorption depends on the band gap of the semiconductor. And this absorption of the solar light can be then used to generate electrons and protons. And these electrons and protons are then used to produce hydrogen and oxygen. So the issue with semiconductors is that you have to use the right band gap to absorb the right amount of photons. And the number of photons in the visible region is very high in the solar spectrum. It's 43%. And one wants to use as many photons as possible falling on the semiconductor device. So one wants to use visible light semiconductors. That means the band gap should lie in the visible region. So most of the studies are on making such materials which are easily, naturally abundant metals, and their oxides or sulfides, and such their band gap should be in the visible region. And the other thing is the semiconductor particle should not allow recombination of electrons and holes. And so the lifetime of the charge carriers which are created on the surface should be as high as possible. These are two things. So one, when you are using only light and doing reactions, it is photocatalysis, or using photovoltaic cells if you make energy out of it. The other thing is that if you also use some electric potential, then you can do electrocatalysis. And when you combine photons and the potential, then you can do what is called photoelectrochemicals. So that is the point. So I talked about band gap. So you must have a suitable band gap in the semiconductor. And TiO2 as such is a very common material, but it is a UV catalyst because it has a band gap which is around 3.3 volts, which falls in the ultraviolet, whereas you would like some things to be in the visible range, say 2.5 electron volts and something like that, so that you can capture maximum number of photons. So a lot of our work is on design of these materials, which will have effective band gap will lie in the visible. So what you want is you want to look at improvement of the efficiency. Ultimately, what you want, your efficiency of the device will be high when all the processes which are involved, from the absorption of the photon to the conversion of charge carriers to the movement of the charge carriers within the within the semiconductor to the electrodes, should be fast, and there should be very little photoluminescence. All these factors will contribute to the efficiency, and the product of these absorption, separation, and transfer will give you the total efficiency. So we need long lifetime of electron holes pairs. We want as many photons to be absorbed, and we want to limit photocorrosion. That means your material should not get degraded in light if it is kept for a long time. So one of the examples that we did was to create a core shell type of structure of two semiconductors. One is a UV catalyst zinc oxide in the core, and the shell is made of cadmium sulfide, silver sulfide, or indium, one of these. So we are made with all of them. This is the band diagram. So the core material has this kind of 2.4 electron volts. The core material has UV catalyst, that is 3.37, and the shell is cadmium sulfide. Now, when we make this shell, then the band diagram shows a certain arrangement of the energy levels. This particular arrangement of energy levels is called the type 2 type of semiconductor system. So two semiconductors which are aligned, whose surfaces are aligned, having the conduction band of one above the conduction band of the other, the valence band of one above the valence band of the other. This kind of geometry or arrangement of the band energy levels is called a type 2 system. This is the synthesis, how we make the zinc oxide, then coat with citric acid, then coat with some cadmium ions and use thioacetamide to bring in the sulfide, and then appropriately heat it to get the cadmium sulfide shell structure. These are the TEM pictures to show you that you have the core and you have the shell, and you can vary the thickness by changing the amount of shell material. And so we have varied from 10 nanometers to 30 nanometers and measured its optical properties and its current generation capacity, right? So the band gap is shifting with the thickness of the shell. From UV, it goes to the red towards 465 from 372. And you can see the photocurrent increases. The red plot has a higher photocurrent for the same voltage compared to the blue, etc. So we can show that the design of the photo catalyst works, and you have a higher efficiency with appropriate shell thickness. Similar thing can be extended to indium sulfide. Earlier we saw that was in using cadmium sulfide shell on zinc oxide. Now we have indium sulfide. This is the high resolution electron micrograph to show the two at the interface. So on one side you have zinc oxide and then you have indium sulfide, and the efficiency goes up in the photocurrent and also in photocatalysis. If you want to degrade a dye, you can see the dye gets degraded much faster when you have the core shell structure. So it is much effective in degrading the dye, and it is much effective in a higher current. Now, this is another design where we are now using two shell materials. So you have a TiO2 core, which is the UV catalyst, and we have a N-type chalcogenide semiconductor, cadmium sulfide. On top, you have a P-type semiconductor. So what we have done is you have a UV photocatalyst, and then on top you have a N-type semiconductor, and then a P-type semiconductor. This design was extended to another three sets of materials. property is the same. This is a UV catalyst, sodium niobate. You have an N-type semiconductor and you have a P-type semiconductor. So different materials, but the objective is the same. And why we did this? Because we are bringing or we are aligning an N-type semiconductor with a P-type semiconductor. Then at this interface, there will be again a charge separation, right? So that is the idea. We'll create a PN junction and that will increase the efficiency of the material. So this is a schematic diagram that if you have the choice of the materials was made based on the energy levels that are known or can be calculated or can be measured using your electrochemical setup. And based on that, we know the energy levels. So this should be the diagram. And then it tells you that if you have electrons created here, that is at the outer layer, which is a P-type silver sulfide, then it will cascade like this, and the holes will cascade in the reverse manner. And you create an electron hole separation with an additional PN junction. So this whole setup or the design helps one in achieving a higher efficiency. Now you can see the way you can measure photocurrent, you can measure photoluminescence to see that how effective is the core shell structure and how effective it is to enhance the efficiency. So one of the things I told is that when you create charge carriers on the surface of the semiconductor, the charge carriers should not recombine very easily. So the lifetime will be higher. And if it doesn't recombine, that means you will not have PL. So your PL intensity will go down. So if you look at these black, red, and blue curves, the blue curve gives you the photoluminescence by the designed ternary nanostructured system, whereas the pure titanium oxide, which is a UV semiconductor, and the pure cadmium sulfide, their intensity, that means the luminescence is much higher in them. And the reason that the luminescence has come down tells you that the lifetime of the charge carriers is high. It is even higher than if you make just one core shell, as has been reported earlier, making a core shell type of structure. That means you have two shells is with a proper, of course, design, which should be those semiconductors based on their energy levels. You can get much lower photoluminescence, and that means higher lifetime of the charge carriers. This is another design. Here, what we compare is that if you have a semiconductor particle, here it is a nanorod, the shape is the nanorod of TiO2, and you put another semiconductor which is in the visible like copper sulfide. If that is uniformly on top of the core material, it has some efficiency. But if it is like particles on top of the rod, but not uniform, it will have a different efficiency. So we compared the core shell type of rod with a composite kind of material. The materials are same, copper sulfide, TiO2. Only the morphology is different. Now you don't have a uniform shell. You have more or less particles on the surface. Then you compare their properties. And if you look at the core shell structure, it has much smaller PL intensity, that is the photoluminescence, which tells you that this TiS2 core shell nano structured material is a better material for your photo catalytic properties and photovoltaic properties. So this is the band diagram which we are shown that what will happen based on calculations. How will the conduction band of TiO2 get slightly modified at the interface, and the valence band of TiO2, how it will get modified. Similarly, the conduction band and valence band of copper sulfide will have some modification at the interface region. And you see that the effective band gap will be in the visible region, right? And so this is band bending, and the effective band gap you can calculate. Okay. Now, this is one more system where we have tried to design such that you have higher efficiency. And this uses the morphology of the nanocrystals. So it is a core shell structure of sodium niobate and cadmium sulfide. And the sodium niobate is the core and cadmium sulfide is the shell. But this core material itself we can make in different shapes. So here we are concentrating on two shapes, where one you are making the cubes and the other you are getting octahedrons. Now, if you have this cube, as you know, in the cubic structure, you will have three, all the facets, all the faces will have same energy in the cube, whether you are looking at the 001 or 100, etc. These are crystallographic planes. Whereas in the octahedral kind of geometry, your planes will have different energy, surface energy, slightly different surface energy. So so this is indexed as the 114 phase, is the 110 phase. So you see these two types of uh, facets will have slightly different surface energies. And so there will be a difference to the electron and hole where it should migrate, because there are two options available here. Whereas here, all the energies are same. So the electron and hole do not have any option. Okay. So this, when you make the core shell, so we make this particle, these are sodium niobate, which are in the core. And on top, now you put cadmium sulfide as a shell. So you prepare the core shell structure, and then you do the measurements. And if you see that if you take the core, which is like the octahedrons, which in the crystallographic notation, the crystal system, one of them it becomes orthorhombic, and the other is cubic crystal system. So there are two words I'm using is the polyhedra. The polyhedra is cubic or octahedral kind of thing. And then the crystal system, you will have cubic crystal system and the orthorhombic crystal system. So the two different sodium niobates will give rise to two different core shell structures based on the two different crystal system of the nanocrystals. And so the properties are different. So if you see this one, which is the cubic phase, it shows this property of the plot of 1 by square of the capacitance. It's a very important plot because it is called the Mott-Schottky plot. And from here, you can tell what are the charge carriers, whether they are holes or electrons, based on their slopes of these plots. So you can see that in the blue one, you have a positive slope as well as a negative slope, right? So whereas in the orthorhombic system, you have only one slope, okay? So it tells you that what kind of charge carriers are present. Are they holes? Are they electrons? It also tells you whether how is the photocurrent. So you see the one of them, the one which has the cubic crystal system has higher photocurrent, right? Whereas the other one has a lower photocurrent. Same thing, you can convert these numbers into solar to hydrogen ratio. And the solar to hydrogen ratio for the one which forms in the cubic crystal system. The cubic crystal system has actually the octahedral facets. Okay, that is the two facets, 114 and the 110. And that one gives rise to higher, around 6% efficiency of the solar to hydrogen plot. Okay, whereas the other one, which is in the orthorhombic crystal system, which is basically due to the cube-like morphology of the nanocrystals of sodium niobate, that has a lower number for this STH, which is the solar to hydrogen ratio. Okay, so now you can see that the design of the particles matter. This is something is very stable, etc. This is the theoretical understanding why this happens. Why this happens is because in one of the system, you create an NN junction, whereas in the other one, you create a NP junction. And this NP junction is a much better, more viable, and gives you more charge separation. The electrons and holes can be separated easily, whereas here the electrons and holes are not separated. They are both on the electrons are both on the on cadmium sulfide, and the holes are on sodium niobate. Okay, so this is not a good design for effective photocatalysis or photovoltaics, whereas this kind of energy diagram is a better system. So these are further calculations, etc. I will not go into the. Now this is another example of how you can design a much more efficient nanostructured hybrid device. So here what we have done, we have taken some graphene oxide based material on which we have embedded cadmium sulfide supraparticles. Okay, cadmium sulfide supraparticles means, like if you look in the picture, there's a round ball made of very small particles. So each small particle is like a quantum dot, right? And together this large particle is called a supraparticle. This is around 400 nanometers. And this each small one is around 5 nanometer particle of cadmium sulfide. And they've joined to form these supraparticles. And you have this particle on the surface of graphene oxide, etc. What it allows you is higher efficiency of one step in this mechanism, which is electron transfer. And the electron transfer increases very largely in a substrate like graphene oxide, etc. So this is the TM FESEM pictures of particles, supraparticles embedded on a graphene oxide sheet. This shows the properties. These are lifetime studies, and you can see that the cadmium sulfide emission gets quenched in the presence of graphene oxide, and the supraparticles, cadmium sulfide 400 means 400 nanometer supraparticles, will decay much faster in the presence of graphene oxide, right? So the CDS 400 in the presence of graphene oxide, if you look at the time resolved studies, then you see it is a much faster decay compared to cadmium pure supraparticle, the blue plot, or the pure cadmium sulfide small nanoparticles. Both of them have much longer. And so basically the electron can be moved away from the site when you have this graphene oxide substrate. I think this may be another design where we are now using two semiconductors for two different reasons. We are using porous silica, which is a very high band gap, not for absorption of photons, but as a support, as an adsorbent to adsorb the organic medium such that the efficiency of photocatalysis goes up. So we design this kind of cup-like structures. This method of synthesis is a little intricate, how you get these cup-like structures and how you get the rim on the surface. So you see this is a TEM where in the core the contrast shows, and then we did EDAX, the core is only made up of silica, whereas the rim has got a deposition of tantalum oxide. Now, why one does this is you want minimum use of an expensive material like tantalum. And so, but tantalum oxide is a very good catalyst. And so you are using the catalytic power of tantalum oxide, but you are using the cost or economy is high because it's only at the rim, and you are using majorly silica to support the tantalum oxide. And silica has two jobs. One is to support the tantalum oxide, and the other is to hold the organic dye which you want to degrade. So the organic dye, here it is shown in a cuvette. When it will degrade, this organic dye will, the color will go away and become colorless. And this we can also use to generate hydrogen. So of course, if you can use the electrons and photons to do degradation of the dye, you can also use them for hydrogen generation. So we use them for hydrogen generation, and you see very high yield of hydrogen. So I just want to show you one slide on microfluidic devices. We make this very cheap way of doing microfluidic devices. We used what is called a laser engraver. It's not very expensive, and minimum lithography you can need. And but you will have channels which are like 50 micron, 100. So they are not in nanometer, but they will be in micron. And you can make these channels, and you can use these channels. It's very simple to make, and then you can use droplets moving within these channels. Of course, but you need a sophisticated camera to take the pictures of the droplets, and the software to run this also. This is and you need syringe pumps, etc. Right. So you can look at this. We can make very fine or thick depending on the way you are doing this lithography. This is very cheap method, the way we have done. We have made the nanoparticles of silver phosphate and also embedded them within the channel. So the silver phosphate is a visible light photocatalyst. And once they are embedded in these channels, you see the yellow color. If we flow a liquid with a dye, the dye will get degraded in normal solar light. So if you use a solar lamp while the liquid is flowing, we can do in situ photocatalysis. So this is the dye degradation you can study, etc. So you can make nanoparticles inside of small diameters and size, like zinc oxide, TiO2, silver phosphate we have made, and you can study the movement of the liquid with the dye, etc. One example of the nanostructured materials we made for heavy metal adsorption on the surface. This I won't have time to go in detail because it's already 11:50. So I'll just tell you that we made this cartridge. You can see on the right side this kind of cartridge. This is a patented thing. And this, depending on the material inside, is a nanostructured material. You can absorb rare earths and also organic, both you can do. And this is patented, already filed, and this was being monitored by. In waste to wealth, we took tin containers. A lot of tin containers are in the market. We took them and we converted them into a catalyst. So, most of the tin is iron and coated with a little bit of tin. So it becomes iron oxide and tin oxide, and that you can use for oxygen evolution reactions. This is waste to wealth. So from waste tin plated steel, we made it in a catalyst which can generate oxygen. This is waste oil, refined oil. We used it to make molybdenum oxide, which is a very good field emitter. This field emitter is MOO2. Field emitter means it can, under high voltage, it generates electrons. This is a student project, BTech students. IIT makes them apply for projects, and then they want them to continue if it is. So this is with undergraduate and master students on used paper cups, which are available in our cafeteria and all, to convert into nanocellulose. And that's what one project we did. So you can do a lot of things like that. I will stop. These are all the students who have worked over several years, and I thank them all and all my current students. Thank you very much. So I'll unshare the slide now.
Yes, sir. There might be a couple of questions from the audience, so they might be required. Slides might be required.
Okay.
Thank you, Professor, for an interesting lecture and very informative lecture. We had touched upon the control of size, shape, and porosity of nanomaterials. We had described the methods of synthesis and functional characterization of the core shell composites, specifically the semiconductor ones, and very interesting work on the supraparticles of cadmium sulfide and the graphene composites, and also the SiO2 tantalum oxide composites, wherein you had also utilized the higher efficiency of tantalum oxide, but minimized its use so that the overall economy of the process also gets enhanced. So in this context, there is a question from one of the viewers. How do we control the thickness of the ring of the tantalum oxide in the SiO2 tantalum oxide spatial structure?
Yeah. So there are many parameters, but one of the main parameter is, of course, the concentration with which you start. So you start with an alkoxide of tantalum, and that the first control is how much are you taking the tantalum oxide in the alkoxide form, and of course, then you will have to worry, because if you read the paper, it's published in Langmuir, and you will see that there are some steps how you use sodium hydroxide, etc. in that.
Thank you, Professor. And on my behalf, I have a curious question. So when we have the core shell composite of the semiconductor material and another material, at the interface, are there any additional resistances to electron transfer or the hole transfer at the interface between the two structures?
Yeah, so it's a very good question. See, the efficiency that we are trying to increase will not be good if your interface is not good. So if you don't have, so the ones which I showed are the best interfaces that we got. But when you do research, you will get lots of interfaces where there will be gaps. There will be, what is very important in physics, they call interdiffusion of ions. That means from one side, ion will move to the other side, and the other side ion will come this side. This interdiffusion you have to reduce. That is a very key point, a very important point. So all the physicists who used to work on simple metals, say silicon with something, these are of course little more complex because chemists work with more complex things. But even in simple materials, so you have two alloys, interdiffusion is a very important thing, and one has to control that. If you cannot control that, then what you are trying to do, make that two semiconductors be segregated, will not happen, and then you will not get the designed effective band gap and the band bending. So that interdiffusion has to be stopped.
Okay.
So the choice of material also sometimes matters, which semiconductors you take.
And a related or connected question to that. So when we saw the difference in the efficiency of the core shell composite, core shell structure versus the composite, the performance of the core shell structures was better when compared to a simple composite. Could this interface be a reason for that as well, Professor?
Yeah, yes. So because in the theoretical study, we are assuming when we are drawing the energy levels we are drawing as if you have two walls against each other, and very well smooth walls against each other. And then actually the theoretical diagram of the two, the way the conduction band of one and the conduction band of the other. If you have particles, then that clear structure will not be there all through the material. So that you will have heterogeneity even in the at the local level in the band drag. So it will not be you will have a local density of states very different compared to the overall thing what you have actually calculated, assuming that the two semiconductors are very segregated and there is a very clear interface.
So there is a question from an MSc student. This has come through a WhatsApp message to me. This little generic question with respect to the area of photocatalysis. The question is, when can we expect industries to adopt photocatalysis as a major source for energy? That's the question that she has put. When do
For
we expect industry
energy.
to adopt?
So actually, photocatalysis is more for degradation of organic pollutants in industry. Okay. So, but probably her question is how to use the solar energy for generation of energy. Okay. So that is photo electrochemical or photovoltaics energy. So, it is already being used, but major industry who have a lot of turnover, they have huge plants, they use at a different level. And very small industries may not use because this kind of technology, etc., to put in place and to have the right kind of engineers trained in this. So it will slowly trickle down. It is coming. You see now in major cities, electric vehicles are coming, right? So industries will be forced to put up charging stations, etc., in cities, right? Indian Oil will do, others will do. So but pressure will come first, it comes in major metro cities where the population density is high, where pollution levels become very high. And then it will slowly trickle down into smaller industries on the rural. But it will happen, it's bound to happen.
There's one more question. What is the advantage that one gets by using microfluidic systems for dye degradation? Because
Yeah,
we could be processing lower volume.
yes. So there the idea was you may have some equipment, okay, some machine. It may be analytical machine, like you may have a LC mass or these kind of equipment, or you may be measuring blood or something, some parameter. Now, in these kind of things, some fluid is flowing, right? And suppose that fluid is generating something which you want to break down. So here we are showing photocatalysis with the organic mean, but I can change it immediately. I can put in urine and I can be doing something else with that in the movement. So in a bioassay, the volumes are very less. So that kind of system, this can be I can extrapolate my understanding there. That's the idea.
There is also one more question from a PhD student. The question is, what is the, or how do the different surfactants act at the electrode surface?
Surfactant.
Yes.
So you have some system where surfactants are there and you are trying to do electrochemistry, probably.
Yes.
That is the question,
Yeah,
right?
that's the question. Yes.
Because when you make nanoparticles with surfactants, we actually take out the surfactants. At the end of the day, you want the nanoparticles. The surfactants are only a medium to get you the right size shape. So you will have to take out those surfactants. But your question is different. That is, in a solution, surfactants are there, and you are trying to do electrochemical. So now it will depend whether surfactant is positively charged, head group, negative. So it will get attracted to that electrode, which is oppositely, right? And then if you have some other reaction in mind, this surfactant may be poisoning the electrode and not allowing that reaction. That can happen. It depends on what is the charge of the surfactant, whether it will go and stick to the electrode or give some other alternate reaction, which is not the reaction you are actually studying. So surfactant can interfere like that.
Let me check if there are. Maybe let us wait for a minute if to see if any other additional question comes. There is a question from one of the faculty members. Could you please describe, or could you please throw a little more light on the interaction between CDS and graphene?
CDS, so CDS the supraparticles we put on graphene, actually it is not graphene. When chemists say graphene, it is graphene oxide. The pure graphene is a different thing. So these are graphene oxides, so they will have hydroxyl groups on the surface, carboxyl group on the surface, and there will be some weak binding with cadmium sulfide. Is that your question? What is your, there is very little binding because of the thio group on the surface. Of course, if you take instead of graphene, you have a silver surface and all, then the binding will become very strong or something. So, okay. Here we are basically trying to use the graphitic oxide, the 2D layers, to act as a sink for the electrons. So the electron will be removed very fast. So you want to take out the electron so that the semiconductor is more rich in holes, right? And so that kind of.
Thank you, sir. That question came via YouTube channel, and the original, I mean, the one who asked the question has also acknowledged the answer. Thank you very much, Professor.
Thank you.
So with this, I formally again thank Professor Ashok K. Ganguli for having delivered the talk today as part of the Science Day celebrations of Shastra Deemed University, Tanjavur. And also I thank all the participants for listening to this lecture. And I'm sure that many chemistry students from different colleges who had seen this lecture would have been inspired by the kind of work that Professor has done, and taking the nanomaterial synthesis to the application level, and then further exploring in the areas such as conversion of waste to wealth and so on. So, sir, your talk has truly shown how a good fundamental science can be useful and inspiring to face or to provide solutions to the challenges that the society is facing, whether it is from the point of pure water or for energy or for management of the waste. And on behalf of Shastra Deemed University, I thank you, Professor, for this talk. And now we shall close the live session. Thank you very much.
Thank you, Dr. Rajan. Thank you, Shastra University, for acknowledging our work, and thanks to everybody.
The only live session is stopped, so probably we can talk a little more.
Okay, sure. I'll just remove the slide.
It's closed.
All right.